On today's video, we're going to learn about antiderivatives in indefinite integrals. So basically, an antiderivative is the inverse of the derivative. So if I were given the derivative function, I ask myself, what was the original function that I had? So for example 1, I want to know what's the original function that has an inverse of 3x squared, which would be x cubed. Because if I take the derivative of x cubed, it gives me 3x squared. But what if it's x cubed plus 5, or x cubed minus 121? So it could be any constant, because remember, a derivative constant is 0. So we write that the antiderivative is going to be x cubed plus c, where c stands for the constant of integration. A function f is an antiderivative of f on the interval of I when f prime of x equals f of x for all x in I. The constant c is called the constant of integration. And so therefore we have a family of functions, and the family of function is represented by big f of x plus c, which is also referred to as the indefinite integral. So indefinite integral and antiderivative are pretty much the same thing. Okay, give it the general solution for the given differential equation. So if the derivative is equal to 2, the original function had to be 2x plus c, because the derivative of 2x is 2. If our derivative function is x plus 3, our original function needed to be 1/2 x squared plus 3x plus c. Okay, your turn. For this example, the derivative is 3x squared plus 2x minus 5. So our original function, our antiderivative, is x cubed plus 2x minus 5x plus c. Integration is the process of finding the general antiderivative. The integration of f of x is the same thing as the antiderivative of f of x. So we're going to learn some new notation. So the notation is the integral of f of x dx is equal to big f of x dx. This elongated s symbol is our integration sign, so that means integral. The function inside the integral is called the integrand, and this is the function that we want to find the integral to, or it's the derivative of the original function. The d of x is our differential, just like we learned in differentials earlier. This is this tells us basically that when this function was figured out, the derivative was taken with respect to the x variable in case of dx. If it was dy, the derivative was taken with respect to the y variable. And then, of course, the plus c that's tagged onto the end of the integral is our constant of integration. Next, we're going to just look at a big long table of integrals that you need to have memorized. It's basically we're undoing our derivatives. So if I'm given the integral that is just a function, just a constant, it's going to be a constant times x plus c. Now if I take constant times a function, that's the same as a function times the constant times the integral of the function. So I can factor out the constant. The integral of x to the n dx is equal to 1 over n plus 1, x to the n plus 1. So in derivative, we subtract the power, now we have to add the power. Now the only caveat is n cannot be equal to -1. If I'm taking the integral of two functions added together, that is equivalent to the integral of the first function, dx, plus or minus the integral of the second function, dx. All right, some trig integrals. The integral of sine of x is negative cosine of x plus c. The integral of cosine of x is sine of x plus c. The integral of secant squared of x is tangent x plus c. And the integral of cosecant squared x is negative cotangent x plus c. The integral of secant x tangent x is secant x plus c. Integral of cosecant x times cotangent x is negative cosecant x plus c. Okay, this is one that we didn't learn, that you probably don't know. The integral of tangent of x is equal to the natural log of the absolute value of the secant of x plus c. The integral of cotangent of x is equal to the natural log of the absolute value of sine of x plus c. The integral of secant of x plus c is equal to the natural log of the absolute value of secant x plus tangent x plus c. And the integral of cosecant of x dx is equal to negative the natural log of the absolute value of cosecant x plus cotangent x plus c. Okay, for exponential, the integral of a to the x dx is equal to 1 over the natural log of a times a to the x plus c, given that the base of a is positive and not equal to 1. The integral of x to the negative 1 dx, or sometimes it'll be written as dx over x, is equal to the natural log of the absolute value of x plus c. And the integral to e to the x is just simply e to the x, because remember its derivative is the same as original, plus the c. We forgot the inverse trig function. So the integral of d of x divided by the square root of a squared minus x squared is equal to the arc sine of x over a plus c. The integral of d of the x over the square of x times the square root of x squared minus a squared is equal to 1 over a, the inverse secant of the absolute value of x over a plus c. And then the integral of dx over a squared plus x squared is equal to 1 over a times the inverse tangent of x over a plus c. Now let's try a few. What is the integral of dx? Well, that's understood to be 1 times dx, so that's a constant, so it's going to be x plus c. You try the next one. The integral of x plus 4 dx is equal to 1/2 x squared plus 4x plus c. All right. I want to figure out the integral of 3x cubed minus 6x squared plus 3x minus 5. So I take out the constant of 3. The integral of x cubed is 1/4 x squared. Take out the constant of 6. The integral of x squared is 1/3 x squared times 3 times 1/2 x squared minus 5x plus c. Simplifying that down, I get 3/4 x to the 4th minus 2x squared plus 3/2 x squared minus 5x plus c. Okay, you try this trig one. Okay, we're bringing the constant of 4 out. The integral of sine is negative cosine of x. The integral of cosine is sine of x. So I end up with negative 4 cosine of x plus 3 sine of x plus c. Okay, I want to bring the constant of 2 out, and the integral of sine of x again is negative cosine of x plus c. So that ends up giving us negative 2 cosine of x plus c. Okay, your turn. Breaking this up to the integral of 1 minus the integral of cosine of theta times cotangent of theta. Well, the integral of 1 is this theta, and minus the integral of cosecant times cotangent is negative cosecant theta plus c, so that gives us theta plus cosecant theta plus c. All right, for these next few, we need to do a power multiple rules of some of the trig functions we had earlier. So I'm going to go back to that last page that we had. I'm going to add a few more rules. And we know that the integral of e to the x dx is equal to e to the x plus c. So what is the integral of e to the ax dx, where the power is a constant times an x? So e to the ax dx. Well, that is simply equal to 1 over a times e to the x plus c. Okay, we also know that the integral of sine of x is equal to negative cosine of x. So what's the integral of sine of a to the x dx? Well, that's equal to negative 1 over a cosine of a to the x dx. A to the x plus c. Okay, likewise, the integral of cosine of a to the x dx is equal to 1 over a times sine of a to the x plus c. And we'll do some of the other trig functions. The integral of secant squared of a to the x dx is equal to 1 over a tangent of a to the x plus c. And the integral of cosecant squared of a to the x dx is equal to negative 1 over a cotangent of a to the x plus c. And the integral of secant of a to the x times tangent of a to the x dx is equal to 1 over a secant of a to the x plus c. And last but not least, the integral of cosecant of a to the x times cotangent of a to the x dx is equal to negative 1 over a cosecant of a to the x plus c. For now, you can just memorize these formulas. And when we get to the substitution method later in this unit, I'll kind of work through why these formulas work out with the a to the x powers, where a is a number, some constant. All right, so now we can do these last 3 examples. So let's look at the integral of e to the negative 10 t dx. So that's going to be 1 over negative 10 times by e to the x plus c. So I'm going to write that as negative 1/10 e to the negative 10 t plus c. Okay, you try the next one. Start by bringing out the 2. And then the integral of secant squared of 2x is 1 over 2 tangent of 2x. And then we're going to have plus our c. So multiplying through the 2, I get tangent of 2x plus c. Okay, the integral of secant of 4 theta, tangent 4 theta is equal to 1 over 4 secant of 4 theta plus c. Okay, so work on memorizing all those integrals from that page. It's just the opposite of the derivative. Sometimes integration is not as straightforward as the ones that we did in the last example, and you'll have to do some algebra first before you can integrate. So I'm going to start by rewriting my radical as a fraction power. Now I have a single denominator. Now, one thing that you need to know about integration, there is no quotient rule or a product rule for integration. So I cannot integrate a constant, a fraction. So I have to break that up. So dividing up my fraction, I end up with x to the 1/2 plus x to the negative 1/2, which now I can integrate using my power rule for integration. And that gives us 1 over 3/2 x to the 3/2 plus 1 over 1/2 x to the 1/2 when I add 1 to my powers. And when you are dividing by fraction, remember you flip and multiply. So I get 2/3 x to the 3/2 plus 2x to the 1/2 plus c as my answer. Now, since my original problem had radical, not fraction power, I'm going to convert this back into radical form for my final solution. Okay. Likewise, in trigonometry, we're going to have to do some simplifying our trig expression. So I'm going to break up my cosine to sine over cosine times 1 over cosine. And I know sine over cosine is tangent of x, and 1 over cosine is secant of x. And then we know the integral of tangent x secant x is just secant x plus c. Okay, you try the next few. Okay, for this first one, we're going to start by rewriting the x to the square root to x to the 1/2. Then we're going to get rid of our fraction, our quotient, by bringing the x term up and making it a negative 1/2 power. Then I'm going to use the power rule by adding 1 to my exponent. And simplifying down, I get 6x to the 1/2 plus c, or 6 the square root of x plus c as my integral. Okay, so for the next example, we got 3 to the x plus c quantity squared. Remember, there's no product rule, and this is 3 to the x plus c plus 5 times 3 to the x plus 5. So we're going to have to multiply this out before we can integrate. So I'm going to use my full method and multiply these two terms together. And that gives me 9x squared plus 30x plus 25 dx. Now I'm going to do my sum and difference rule and my power rule, and I'm going to end up with 9 times 1/3 x cubed plus 30 times 1/2 x squared plus 25x plus c. Simplifying this down, we end up with 3x cubed plus 15x squared plus 25x plus c is my integral of the original problem. Okay, now let's try this trig one. So I'm going to distribute the secant y to each term in parentheses to get rid of the parentheses. Then I'm going to use my difference formula and do the integral of the first term times the integral of the second term. The integral of secant y tangent y is just secant y. The integral of secant squared y is tangent y. And then plus c. So we get secant y minus tangent y plus c. The last thing we're going to learn is something called finding the particular solution to a differential equation. So in many applications of integrals, you will be given information to determine a particular solution. So remember that plus c represents a family of solutions. Many equations work. Now we're going to figure out only a single equation that works. To do this, you need only to know the function for the value of the function at one value of x. And this is usually referred to as the initial condition of the function. So we'll learn this through examples. I want to figure out the particular solution to that satisfies this differential equation. So I've given the derivative is equal to 6x. So first I need to find my original function by figuring the integral of my derivative. So I need to figure out the integral of 6x. So bring the constant out, and then the integral of x is 1/2 x squared plus c. So that gives us 3x squared plus c is our f of x. Now I'm going to use my initial condition of f of 0 is equal to 8. By replacing the f of x with 8 and every x with 0 in my function equation. So we're going to go 8 is equal to 3 times 0 squared plus c, and then we're going to solve this equation for c. And we end up that c is equal to 8. So therefore, my original function, or the particular solution to this differential equation, would be 3x squared plus 8. Okay, I want you to try the next example. Okay, to find our original function, we need to find the integral of f prime of s. So we're going to integrate 10s minus 12s squared x cubed with respect to ds. And so bring the constant 10 out, the integral of s is 1/2 s squared. Bringing the constant negative 12 out, the integral of s cubed is 1/4 x to the 4th plus c. Simplifying that down, I get 5s squared minus 3s to the 4th plus c is equal to f of s. To find the c value, I'm going to use my initial condition of f of 3 equals 2, replace f of s with 2 and every s with 3. Simplifying this down and solving for the c, I get that c is equal to 200. So therefore, my particular solution to this differential equation is f of s is equal to 5s squared minus 3x to the 4th plus 200. In some cases, you're given the second derivative, not the first derivative. In this case, you need two initial conditions, one for the first derivative and one for the original function. So I will start by, if I integrate the second derivative, that'll give us our first derivative. So the integral of x squared, which is equal to 1/3 x cubed plus c1 is our first derivative. I'm going to use our initial condition for the first derivative to solve for c1. And I get that c1 is equal to 8. So therefore I can say my derivative function, f prime of x, is equal to 1/3 x cubed plus 8. Now to find my original function, I would simply integrate my first derivative equation. So f of x is equal to the integral of 1/3 x cubed plus 8 with respect to dx. So f of x is going to be equal to, bring the constant 1/3 out, times 1/4 x to the 4th plus 8x to the 4th, 8x plus c. That parentheses in the wrong place. So f of x is equal to 1/12 x to the 4th plus 8x plus c2. Now to find c2, I'm going to use my second initial condition for the original function, replacing f of x with 4 and x with 0. And I end up that c2 is equal to 4. So therefore, my conclusion is the original function that meets these conditions is the function 1/12 x to the 4th plus 8x plus 4.